Hello and welcome to episode number 23 of CS350 Online. I'm your host as always, Leslie Eisted. In today's episode, we're going to wrap up all of the topics that we've talked about throughout the term by talking about virtual machines. And it's going to be a really brief introduction to virtual machines and what they are and how we use them and why we use them and all those wonderful things. So hopefully that will prove interesting to some of you. There's no readings for today, but you are welcome to read more, of course, on the internet if you so choose. There's lots of great resources that are out there. We can provide them on Piazza if you're really interested. In terms of things that are left to do for the term, don't forget about assignment 3, of course. And the page table component, even though it is on the marking report, we simply haven't updated the marking report. You are not responsible for implementing the page tables. So please make sure that you don't do all that extra work because it's so not needed. The other thing is to remind you to do your Learn quizzes and the reading assignment. I think the reading assignment is due tomorrow, but I could be forgetting the actual date. I never remember what day it is. That's the truth. I don't know what day it is. So just make sure you're not forgetting them. It would be a shame to miss out on those marks. Okay. Yeah, it says it's due tomorrow at 11:30 p.m., so July 30th. So make sure that you get that reading assignment in. And then, of course, it's just the remaining quizzes that we have, and you are welcome to do them whenever, but I would recommend that you don't leave them to the last day. So the exam period begins on like August 7th, and all of their quizzes are going to be due on August 5th. So there's a couple days leeway there, but I don't want you to leave it to the last minute and then be panicking about things, because nobody likes to panic, right? All right, so, and by the poll on Piazza, it looks like the preferred final episode is to do a brief intro to networking and the operating system. So that is what we will do on Tuesday of next week, and hopefully you will find that interesting. And of course, the other video about how to design your own operating system will be posted as well, so that if that was what you preferred, you can still have access to that. All right, now this is our last OS of the day because it's the last OS of the day. So I've saved something rather quirky for the last day. And hopefully you'll find it interesting. Some of you probably already know which OS it is. And the OS, of course, is called TempleOS. And TempleOS is an operating system that was released in 2013, and it was created by a single guy. His name was Terry Davis. And for those of you who have heard of TempleOS before, you know that its creator is no longer with us. He died, I don't remember. It was a few years ago, not too long ago. 2018 is when he died. So about 3 years ago. I believe he was hit by a train. Don't walk on train tracks. It's not always a good idea. But the story of this operating system is actually, it's very interesting. So there was an operating system that actually predated this that was from the same person, but 2005, and that was called the J operating system. But it wasn't turned into TempleOS and updated significantly in 2013. But here's the story of this OS, because it's a bit of a quirky story. So the developer, Terry Davis, was actually quite manic, and that happens. Sorry. And at one point in his life, he was considered an atheist. But during one of his manic episodes, or after a series of manic episodes, he became incredibly religious. And he believes that he was asked through these manic dreams or episodes to create an operating system that would be God's official temple. And the specifications came as explicit instructions, according to Davis. So apparently, God stated that the screen should be 640 by 480 pixels. There should be 16 colors and only one audio voice. There should be no network, because why would you need to talk to anybody else? One address space, because there's no concept of hiding information from other processes. Everything should run in kernel privilege, because why would anybody try to harm God's temple? And it should be a modern operating system in all other aspects. And this operating system might seem very silly, and the premise might seem very silly. But from a technical perspective, this is actually a very interesting operating system. And by the way, it's open source. You can go download the code to it. It's not that much code. I think it is like 127,000 lines last I looked. That's not bad. I don't know. Maybe that seems like a lot to you, but compare that to the Linux kernel. It's like a fraction the size. I mean, you've got preemptive, concurrent, multicore support. It's a fully concurrent operating system. You can run things at the same time. But it's these two things here that really make things interesting. It's the fact that it has one address space shared for all processes. That makes things very interesting. So you're not using virtual memory. You're actually just using physical addresses. And whenever you need memory, you just grab physical addresses that are available. So your core map, it's just a core map, and everybody uses it directly. And I mean, there's advantages to this, obviously. I mean, you've seen how much work it takes to do system calls. You know that they're not fast. So if you get rid of the concept of system calls by having one shared address space and everything running in kernel privilege, then without the system call code, everything is actually much more efficient. It runs faster because you don't have to throw exceptions and then respond to those exceptions and, save and restore contexts all the time. So that's really interesting. And the other thing is, because processes can directly communicate with each other, the operating system doesn't have to get involved there either. So these two features right here actually make the source code of this operating system very, very interesting and actually really simple compared to even OS 161, because we don't have system calls. There's no need for them. Now, there's some interesting details. So, for example, hardware is expecting that, like your MMU and your CPU are anticipating that addresses that they see are virtual. So if your operating system isn't using virtual memory, then how do you pass addresses to the MMU and have them translated? Well, it's simple. You do a unity mapping. So it's like it's an identity. That's all it is. So you still have to do that because of the hardware's limitations, but the mapping between virtual and physical addresses will just be the identity. So, I mean, there were little challenges he had to overcome in order to support these two features because they're such unusual features, but he was able to overcome them quite easily. Now, the operating system itself is very, very simplistic. Obviously, I mean, you've only got a 640 by 480 screen, so it's like VGA graphics from like the early 90s. 16 colors, so if you want to get more colors than that, what you had to do is dithering, and that doesn't look so good anymore, especially if you've got a nice big screen. But he also had some other things that he did for this. So, for example, he actually wrote his own version of C, which is called Holy C. And that's an interesting thing on its own. And you're welcome to look up that. But Holy C has some very interesting features. And then he wrote TempleOS in that. And then he created his own file system called the Red Sea, which is kind of, I think about this name for a file system. So actually, that's a pretty cool name for a file system. Because when I think about file systems, something you also think of is partitioning. And, you part the Red Sea. So, kind of funny. It also had things like an oracle, which let you communicate with God or something. It's, from a technical perspective, this is a very, very interesting operating system. So, just to show you what it looks like, this is I want to tell you, this is an operating system. From a technical perspective, it's very interesting. Is this an operating system you're going to download and use? Probably not. Without a network, with such low screen resolutions, doesn't really make a lot of sense for people to use it. Without any security, it doesn't really make sense for people to use it. But again, from a programmer's perspective, it is very, very interesting. And I do recommend that you actually take a good look at it. So what did it look like? Well, we can show you what TempleOS looks like. So this is TempleOS. And as you can see, it's very, very simplistic. You've got the 640 by 480. You've got 16 colors. You can see the dithering here, trying to create some different levels of shading. You can actually see what's going on because everything is open. There's no concept of user versus kernel privilege. This actually makes it really interesting. We can actually watch the operating system do every read and every write and so on. So it's a really, really, really interesting way of doing things. And again, you can actually get this source code for this. Let me just bring it up here because I do recommend you take a look at the code. So there's the website for it. It's templeos.org. And you can download it from here. And I believe the source code may also be posted here as well. Now, one word of warning for those of you who are not familiar with this individual. He does have a series of YouTube videos. They were taken off YouTube for a period of time just before his death. And I think after his death, somebody put them back. I am not advocating that you look at those videos. He was a very strongly opinionated individual, and those opinions may not be very nice or friendly. So I am only going to talk about TempleOS from the perspective of its technical, interesting issues. And I'm only suggesting that you look at the source code simply because of the fact, here's an OS that doesn't use system calls. So that's really interesting. I would recommend avoiding the YouTube videos. All right. They're pretty much going to offend everybody, is my understanding. I haven't actually watched them myself, but I've heard they're quite offensive. All right. So what are we doing today then? So that's our final OS of the day. And I mean, sure, there's lots of other OSs we could talk about, but we're going to call it quits there. For those of you who are wondering, the OS of the day is not something that we will test you on. I just do that because I think it's kind of fun to see where we have come from and where we are today. And especially in today's world where, realistically speaking, there is not a lot of choice in operating systems. You're either using a Windows machine, a Mac machine, or you're using some kind of GNU Linux machine, or you're using a cell phone. So there's only like 5 choices that people can make. And with those just 5 choices, and they're all being really, really big, it's easy to forget that there might be others out there. So I think it's really fun to just see what they are. Also, I like computer history, so it's kind of fun looking at OSs that existed like 40 or 50 years ago. Because, it's fun. All right, so today what I want to talk about is virtual machines. And the reason why I want to talk about this is because in order to learn about a virtual machine, there's a whole bunch of stuff that you need to know about that kind of sets off as a review of the whole course. Now, I'm going to assume that many of you are actually familiar with virtual machines. Some of you, let's just open a Chrome up here, might be familiar with the one called VirtualBox. And this isn't actually a virtual machine itself. This is a hypervisor, and we'll talk about what that means in a few minutes. And if you haven't used VirtualBox, which I actually haven't used VirtualBox, when I was in undergrad, the CS Club had free licenses to VMware, which is a very big supporter of virtual machines. And this is actually what I'm accustomed to using, so VMware. And I don't know if you can still get a license to this through the CS Club or not, but you used to be able to. But VMware was one that you would run on Windows, and then you could install Linux right inside of it. And then, of course, there is also, for those of you who are using any kind of Apple product, a lot of people use this Docker. I actually haven't used Docker either. I tried to use it, but it didn't seem to do what I wanted it to do, at least not in a traditional sense. So when we think about virtual machines, a lot of people are going to be thinking right off the top of their head using VirtualBox, using VMware, or using Docker. But they're not virtual machines themselves. So let's actually start talking about what a virtual machine is and why we would use it, and some of the really interesting issues we have had to solve in order to do the tasks that they do. I'm just going to minimize that. So when we're talking about a virtual machine, what we're really saying is this is a fake computer. This is a simulated, it's an emulated computer. And we do this in all different kinds of ways, and we have done it in all different kinds of ways for many, many years. For example, CS350 that you've been using to run OS 161 is a kind of virtual machine. It is an emulated computer system. It's not real. You don't have a MIPS R3000 in your desktop right now. I mean, it'd be really cool if you did, but you don't. And in fact, the MIPS R3000 dates back to, I think, the late 80s. Most of you, unless you have like a PlayStation 1 or a PlayStation 2 kicking around, you probably don't have one of these chips. I don't have my PS2 anymore. And yes, a MIPS R3000 was in a PS1. That was its primary processor, and it was a coprocessor in the PS2. But CS161 is just a simulated version of that. But how does that work exactly? So we are running OS 161 on top of this simulated computer. So we're taking assembly instructions from MIPS and running those assembly instructions from MIPS on this simulated computer, which is running on a different architecture altogether. So you might have an AMD architecture, or maybe you have an Intel architecture that you're running it on. While there are some, or maybe you have an M1, who knows? How does that work exactly? So that's one kind of a virtual machine. It's kind of an old-fashioned kind. And we'll talk about that, how that kind of works in a bit. But there's other kinds of things that you can do with virtual machines, like other types that we've used before. So I don't know about you, but when I was a kid, I didn't have a Nintendo or a Super Nintendo or anything like that. And so I didn't actually start playing Nintendo and Super Nintendo games until I actually came to university. And of course, one of the problems with these old Nintendos was the fact that the cartridges, maybe you're not familiar with old Nintendos. Let's bring up a Super Nintendo. Super NES. So if you're not familiar with the original Nintendo system, you can actually just look it up. It looks like this. It's not very exciting looking. There you go. There's a Super Nintendo. Oh, this might be a new version of it. Yeah, that's the new version. That's not what we want. But the original Nintendo systems actually had a cartridge-based system. So the game actually is a circuit board inside this little box, and it plugs into the actual console. And one of the problems is that on the cartridge itself, where the PCB actually connects into the Nintendo, it can get really dirty. And so one of the things that you will actually see, and maybe you've seen memes of this, is people blowing on these cartridges, because the idea was you blow on it and then you put it back in and it would work. And I don't know the reality of it working, but it was a pain. And so a lot of people in the 90s and the early 2000s, instead of using the actual physical hardware, which suffered from a number of problems, they would use an emulator. And the emulator was effectively a virtualized computer system where it took the binary files that would have been on those cartridges and it's going to play them on this virtual Nintendo on your computer. Well, that emulator is a kind of virtual machine. A very simplistic one, but a virtual machine nonetheless. And what a virtual machine does for us is it gives us the ability for a particular architecture to act as other architectures or other systems. So for example, sys161 lets us run MIPS R3000 code on whatever architecture we have. And things like Nesticle, which is one of the NES emulators, lets us run NES games, it's the original Nintendo, on your home computer. So that's what virtual machines are giving us the ability to do. Now, what's interesting is they actually give us the ability, there's many, many reasons why we might actually do this, and we'll talk more about that at the end. But the idea is, ideally, how these should work is that you have a virtual machine, and then all of the operating systems and programs that would run on that virtual architecture should be able to run on that virtual machine in isolation. And in fact, what that means is that the operating system, OS 161, should not be aware that technically speaking, it's running on a fake R3000. Shouldn't be aware. It shouldn't need any patches. It shouldn't need any modifications whatsoever. Now, we're not so good at that part. So for example, back in the day when I used to use VMware for a lot of things, you'd install VMware, which was like a virtual machine manager. And we'll talk more about exactly what it is in a bit. But you would install that, and then you would use it to create, your Linux virtual machine or your Windows virtual machine or your Hackintosh or whatever it is you're trying to create. And then you would have to, after you've installed that onto the virtual machine that you created, this virtual architecture, then you would have to install some patches or some tools and utilities so that the virtualized operating system could actually interact with the underlying one. So ideally, any software that's installed on a virtual machine should run in isolation and not be aware in any way that it's running on fake hardware. In reality, a lot of the tools we actually use do actually use some patching, and some driver support has to be added to get the full experience. So we're not that good. Now, this idea of having a virtual or simulated computer actually goes all the way back to the 1960s. It's a really old idea, but it didn't really take off. And most of the reason for that was because in order to do this, your computer actually has to be really good. And like from a performance perspective. And if you look at computers from the 60s through to the 90s, computers were not that good. And in particular, in order to do a lot of the tasks that we need these virtual machines to do, we actually needed hardware support in order to help solve certain problems. And architectures before 2005 didn't offer the hardware support, and so it was just too slow to actually run the virtualization. So VMs actually came back after 2005, and they've been pretty popular ever since. And in fact, I don't know how many of you have ever used Amazon AWS services, like the EC2 cloud. When you do that, you're actually creating a virtual machine on Amazon servers. So it's pretty popular now, but it wasn't for a long time. So just to review some of the different tasks that we need to do before we dive into what are these virtual machines doing and how are they implemented? How do we make one architecture behave as another? Remember that your computer actually consists of a whole bunch of different devices, and this is important here. So you've got a CPU, which is your processor. It's got an MMU inside of it, which does the address translation. Yes, even the MMU is going to come into play here. We've got RAM, and we've got things like keyboards and mice. You've got microphones and cameras, and you've got all kinds of things that are actually plugged into the system. And we know that our CPU is going to be able to execute the instructions that are given to it, and that some of those instructions may be privileged, and some of those instructions might be not privileged. And we use the privilege of the CPU to make that distinction so that if the CPU tries to execute something that was privileged during an unprivileged state, it will actually throw an exception, and the operating system will respond to that exception and actually, throw the appropriate error code, panic, or however it believes. So our operating system then is actually going to handle not just those kinds of interrupts and exceptions, but every kind of interrupt and exception. And here's something to think about. If I've got an operating system, let's say I install some VM hardware or some VM software on this machine that I'm using right now. Okay, that's great. So I've got Linux, it's Kubuntu, running natively. And then let's suppose I install Windows 3.1 inside of a virtual machine. Okay. If I push a key on my keyboard and it's the operating system's response or responsibility to respond to an interrupt, which operating system responds to the interrupt? Which hardware, who gets the interrupt? There's a lot of really interesting problems here. So remember that interrupts are actually signals, electrical signals that are raised by the hardware itself because the hardware needs some kind of attention. So maybe it's done a task, maybe there's an error. That's what they do. And exceptions are raised by software. Now, MIPS treats interrupts and exceptions as the same thing. That's not necessarily true for all architectures. So some architectures actually distinguish from them in architecture, whereas we don't for R3000. So what kind of exceptions you know about system calls? And I'm sure you've gotten your fair share of TLB misses, which are errors with memory, reading and writing and accessing different regions of memory. But it's also things like instructions, invalid use of instructions. Our operating system also creates the execution environment for the user program. What does that mean? It creates the process. So that's finding memory for the address space, loading the program into the address space, creating a thread, adding a file descriptor table, and all of those things. So that's creating the execution environment for the program. The operating system is going to manage memory. That's the core map that you're working on in A3 right now. And our operating system is also going to implement concurrency in some way, maybe. So maybe it does cooperative concurrency, or maybe it just does preemptive concurrency. So there's lots of little things that we need to think about here. So let's try to implement this. This is actually a very simple way of doing it, and a lot of the emulators I've actually talked about already do it in this very, very simple way. So the virtual CPU is just going to take some instructions and it needs to execute them. Well, since I don't actually have a physical piece of hardware, maybe what I could do is for each instruction that I receive that I'm supposed to execute as my R3000, maybe instead of actually executing them directly, since I'm not real, maybe I could just translate it to the host CPU's instruction set. And that's actually what CS350 is doing, is it captures each of the assembly instructions from MIPS, and it's going to translate them to instructions for the host CPU. So looking down here at this little diagram, you'll notice I keep using the word host. So you have your physical CPU. That is your host. That is the actual bare metal in your computer. And sitting on top of that is an operating system, and that is the host operating system. It sits on the bare metal. And then the virtual machine sits on top of the operating system, which means it runs as a user program. Interesting, right? And then your operating system, your guest OS, like OS 161, runs on top of the virtual machine. So we have hosts and we have guests. So this seems very simple, right? To implement CS161, we just take each of the assembly instructions we receive from the guest program, the guest OS, and we're just going to translate them into instructions for, well, my computer I'm using here is a Ryzen 9. So we're just going to translate them to AMD's assembly instructions. But it's not that easy. And the reason why it's not that easy is because we haven't discussed how interrupts are handled. So for example, when I push a key on my keyboard, that is going to send a signal to the physical CPU, which is going to be picked up by the host operating system. But what does the host operating system do with it? Is this key press for the host Or does it need to forward it in some way to the guest operating system? How is it going to make it so that a virtual interrupt gets fired on this virtual machine so that this guest operating system can actually respond to it? Then we have issues of privilege. If you look, this guest operating system, OS 161, should be operating in privileged mode, and yet it's running as a user program on Linux. So if I am in sys161 actually translating privileged instructions to such as disabling interrupts on the CPU, if I translate that to the equivalent for an AMD chip, guess what's going to happen? Well, it was a user program that did that translation. So when it tries to execute on the physical CPU, we're going to get an exception of an illegal instruction or invalid permission. So how do we handle privileged instructions like disabling interrupts or writing to files? How do we actually handle that? And then there's an issue of virtual memory. Because the guest operating system is going to implement some kind of virtual memory, and the virtual machine is going to actually want to make those translations, but these two both run in user privilege to start with. So that raises some very interesting issues. So how could we handle some of these issues? Actually, it's not that bad for, a simple emulator. For one, and again, this is still our first attempt at making virtual machines work. So the first thing that we could do is to handle privileged instructions. What are we going to do? Sorry, we've already talked about this slide. One of the things that we can do, by the way, for privileged instructions, like disabling interrupts, is that when you are actually, I'm just going to use this slide instead of the next one. When you're in sys161 and you receive a privileged instruction, you can't translate that privileged instruction to the host operating system because it's going to throw an exception because you're a user program. What you need to do instead is recognize that these privileged instructions are part of system calls that you actually want to make to the host operating system. So between the guest operating system and the virtual machine in this model, we actually need to detect when we're trying to do a system call, and we need to translate that system call to a system call for the host. And that's how you can bypass a lot of these privilege issues, is by just saying, oh, I see that you are actually trying to write to this protected region of memory. Okay, because you want to talk to your printer. So what you would do is you would recognize that and capture it and translate it not to raw assembly, but you would translate that to a system call for the host operating system. A little bit trickier, obviously. And so that's one of the ways that you can handle things like privilege. But what about interrupts? How do you handle interrupts? There's different ways you could do it. You could do interrupt forwarding. So each virtual machine can actually register with the operating system that they are waiting for keyboard input. And so when the host operating system receives the signal for the keyboard input, if the VM is in the foreground and it's active, then the host operating system can forward that interrupt to the VM, and the VM can create an artificial interrupt for its host, guest operating system. So that's one way that you could do it. What about virtual memory? Well, why is virtual memory a problem here? It actually comes down to the issue of, so since both the host and the guest operating system are running in virtual memory, what if you end up having address collisions? Because what if the host and guest are using the same mapping for different things? So you've really got to make sure, in order to prevent that, that the guest and the host are both implementing virtual memory, and that the guest operating system is under the impression that the addresses that it gets for its memory are physical, even though they're not. And then you need to make sure in the virtual machine, when you're doing address translations or when you're translating instructions, you need to make sure that you are taking the addresses from the guest operating system, translating them to the virtual addresses for the user program in the host operating system for every address that you do. You can see here that in order to make a VM work, you've got to translate all the instructions, number one. You've got to capture system calls and forward them, but you've also got to do an extra layer of software-based address translation. It's not so nice. It's the reason why we haven't really used VMs until the last 15 years, 16 years. All right. So that's kind of a naive approach. It's also kind of how we do things as a user. So let's take a little bit of a deeper dive on some of the terminology with respect to virtual machines. So first off, you've heard me mention the word hypervisor. This is a piece of software that manages the virtual machine. So VMware is a hypervisor. VirtualBox is a hypervisor. Docker is a hypervisor. These are all hypervisors. And what they do is they let you create virtual machines and manage those virtual machines. Like when you're creating a virtual machine, like what CPU would you like and how much memory would you like for it? And it actually sets that up and it's going to manage it. So for example, VMware, if you were running it on Windows and you created a Linux VM, or a VM that you're going to use for Linux, then it's going to have, as its virtual CPU, a very standard CPU. So you're probably going to choose like an Intel architecture. What's nice about that is you don't have to translate the instructions themselves, but you do have to capture things like system calls. So the hypervisor is going to let you create the virtual machines, but also manage them. So make it so that they share resources fairly and all of those things. Set up file systems and so on. There are, as it turns out, two different types of hypervisors, and the kind that I have spoken about so far today and is type 2. So a type 2 hypervisor, which is what most of us have used, is something that sits on top of the host operating system, and it operates as a user program. So VMware, Docker, VirtualBox. For consumer, those are operating as type 2 hypervisors. And then the virtual machines will sit on top of that hypervisor because they are created and managed by that hypervisor. And all of the stuff that we've actually talked about so far, you know, how do you handle privilege? How do you handle virtual memory? This is all with respect to either a virtual machine running directly on your host operating system, i.e. the virtual machine itself is its own standalone thing, so like Sys161 or Nesticle or anything like that, an emulator. And all of these issues here, this is with respect to a type 2 style hypervisor. And the same is true. So when we're talking about using VMware, it's roughly the same set of issues you have. How do you deal with privilege when you are running in an unprivileged state as well? And the issues are the same. So there we have what most of us have used, which is the type 2 hypervisor running as a user program on the host operating system. So the type 1 hypervisor, which is something you might have used in industry, actually is different. And it actually runs almost like its own operating system right on the bare metal. So the operating systems don't run on the bare metal. There's no host operating system. The type 1 hypervisor runs directly on the bare metal, and then the virtual machines will be created and managed by that type 1 hypervisor. And these have issues of privilege as well, because the type 1 hypervisor running on the bare metal is obviously going to run with full privilege, but then how do you get these virtual machines here to execute issues of privilege? How do you get these to make sure that their virtual memory isn't overlapping? Because now this type 1 hypervisor, I mean, its job is not to implement virtual memory. Maybe it needs to in order to handle and prevent collisions. And then how do you handle things like interrupts with this particular system? So with the type 2 hypervisor, the host operating system can forward interrupt signals to the hypervisor, who can then pass it to the correct VM. But how is that going to work in this other model? So again, we've really already talked about the type 2 hypervisors as they run in unprivileged mode. And unprivileged instructions, and I didn't say this before, they can just be directly translated. It's only the ones that would be privileged instructions where the hypervisor is going to have to be, oh, you're trying to write to a disk. And the hypervisor, not the VM, the hypervisor would actually be responsible for emulating the behavior of those privileged instructions and making the appropriate system calls. So, what does a type 1 hypervisor do with privilege? Well, here's the thing. We know that the type 1 hypervisor is going to run in privileged mode because it's running on the bare metal. But the VMs are going to run in less privileged mode, so they're not going to be allowed to disable interrupts. They're not going to be allowed to do a lot of things. Unprivileged instructions can execute normally. Now, what that might mean, so if the architecture of the bare metal and the architecture of the VM are the same, then no translation is required and we just directly execute. If we do need to do some translation, the hypervisor would actually do that. But what do you do with privileged instructions on a type 1 hypervisor? So first off, the hypervisor is going to have to catch all of the privileged instructions coming from the virtual machine, and then it's going to have to decide, how do I handle them? So it might choose to just pass them right through. So for example, if you're trying to write to a disk, it might just pass that right through. It might just be, okay, yep, this is fine, you can execute that. But sometimes it can't do that. So for example, if the VM wants to turn interrupts off on a type 1 hypervisor, do you really want it to do that to the actual CPU? What if there are other VMs running? Because you might actually have multiple worldviews. Worldview would be the VM you are using right now. And if you have multiple VMs, when you, there could be other VMs running at the same time, different worlds. And if you disable interrupts on the bare metal, then you kind of disabled interrupts for everybody, even though the other worlds didn't want that. So the hypervisor is going to have to decide whether it passes the privileged instructions through to the CPU or whether it's going to simulate the behavior of those. Regardless of which kind of implementation it does for privileged instructions, the type 1 hypervisor is going to make sure that the virtual machine believes that this has happened. So it's going to have to make sure that the VM is not aware that it may not have actually happened. But then we get a really interesting problem. The interesting problem is that the operating system, the guest operating system, running on the VM for a type 1 hypervisor is going to run in unprivileged mode, just like the VM itself is running in an unprivileged mode. And then the user programs running on the guest operating system are also running with no privilege. So let's suppose that a user program that is running on our guest operating system tries to do something bad. Let's suppose the user program tries to alter the voltage of the CPU without permission. It didn't use a system call to try to do it. So what happens? Because here's the thing. The guest operating system and the user program on the guest OS operating system are actually running with the same level of privilege. So the hypervisor doesn't know, the VM doesn't know whether it was the guest OS doing this or the user program on the guest OS doing it, because the hypervisor doesn't know what the guest OS is doing. It doesn't know what the VM is actually doing. So how does it know whether this should be an instruction you allow to happen or one that you throw an error? You're not allowed to do this if the two programs are running in the same privilege and you can't actually differentiate between them. Well, the answer actually comes from the fact that your CPU doesn't have just two levels of privilege. And, for most people, 2 isn't all you need, unprivileged and privileged. But once you start introducing hypervisors to the mix, we need to start using some of those other rings of privilege. And that's exactly what we're going to do here. So the hypervisor will run in complete privilege. And then the VM in the guest OS will run in the next level of privilege, so that the user programs running on the guest operating system can run with no privilege. And that way we can actually differentiate between the OS asking us to change the voltage and the user program asking us to change the voltage. But in order to do this, your architecture has to support different levels of privilege other than 2. And most architectures these days actually do support multiple levels. So your computer sitting in front of you probably has 4 levels. That's pretty common. Pretty neat. Seems like a pretty easy solution. Now, what are we going to do with virtual memory? So dealing with this on a type 2 hypervisor is actually not that bad, because what you're going to do is the virtual machine is going to treat the address space provided by the host operating system as physical addresses, and then the guest operating system is going to take what it believes are physical addresses but are really just virtual ones, and it's going to then implement its own virtual memory translation scheme on top of that. So you're going to get multiple levels of translation going on there, but as I said, the reason why we haven't used VMs until fairly recently is because there's performance issues. But what about a type 1 hypervisor? How are we going to implement virtual memory using type 1 hypervisors? So here's the thing. You could take your physical RAM and just carve it up. Okay. VM1, you get this chunk of physical memory. VM2, you get this chunk of physical memory. VM3, you get this chunk of physical memory. You can do that. And then inside of that VM or inside of the hypervisor, it might perform some kind of mapping so that each VM believes that it is the king of the world and it only sees from 0 to however much RAM the hypervisor wanted to give. Or, to be a bit more efficient, you could actually have the type 1 hypervisor implement its own page tables. Regardless, the type 1 hypervisor actually is going to manage memory in some way to ensure that physical collisions between the memory used by each of the virtual machines doesn't actually collide. Which means that the hypervisor itself is going to be involved with address translations. So it's either going to be trying to do some kind of dynamic relocation where it says, oh, I see this address here, which is like from VM1 maps to this physical region here. And this address here goes to this region here. So it's going to either do something like that, or it's going to do paging, which is what they actually do. And it's going to implement a shadow page table. So that means that if your VM is using a 4-level page table, there's a secret 5th level implemented by the hypervisor to make sure that the physical memory that's used by one VM doesn't collide with the physical memory used by the other VM. So we use this shadow page table. Now, that would mean if we have a shadow page table that every address translation actually has to be done by a hypervisor instead of the MMU. And that's really bad. We don't want to do that, and we already know that, because if we tried to do that just with a regular system, that means that the software is involved with every address translation, and the performance of that is going to be terrible. We know that. So how do we solve that problem? Well, this is one of the reasons why we also haven't been doing VMs until the last 15 years, is because we needed hardware support to help us here. Having the hypervisor do the address translations for everything, that's really, really slow. And so what we actually needed was our MMU to have understanding or the ability to support shadow page tables. And modern CPUs, so the Intel Nehalem architecture, which is the first generation i7s, and onwards, their MMUs actually support something called extended page tables. And this is not a feature that you would really use unless you were using Type 1 hypervisors. And what it lets you do is it can actually translate the guest virtual address to the host physical address directly. So it is actually able to perform the address translation for the shadow page table in the hypervisor as well. So that's really, really nice. Now, what happens if you have an exception? If you get an exception, if the exception is in the user page table levels, then it's probably going to be forwarded to the appropriate VM. But if the exception is in the shadow page table, then it's the Type 1 hypervisor that would actually be handling that. Otherwise, the hypervisor would just forward that to the appropriate VM. Now, here's the interesting thing. So having the extended page tables, you can essentially imagine it as now you have two page table based registers. One is for the guest, and one is for the host. And so you end up with this interesting issue of what happens when you swap worldviews. So that is, what happens when we go from running VM1 to VM2? Well, now we also have to update the MMU to change the page table based register for the shadow table as well. So we're going to have to make sure that the hypervisor is keeping the MMU up to date on the shadow table it's using, so that we are actually using the translation for the right VM. Doesn't sound so bad, right? I think that's really straightforward. What do you do about those devices, though? So, one of the things that we had talked about in this course was actually I/O and devices, and we spent a fair bit of time on it. How are you going to handle file systems for all of these different VMs? There's lots of different ways that you can actually do it, and a Type 1 and a Type 2 hypervisor actually do this a little bit differently. And they don't have to do it differently. They can both use these models. So one strategy that you can use to have a file, like a disk for a VM, regardless of whether it's running on a 1 or a 2 hypervisor, is to partition your physical disk. Like actually physically partition the disk. So, you have a partition that's 512 megs, and that is for VM1. And you have a partition that is 65 megs, and that is for partition 2, or VM2. And then each VM only keeps track of its particular partition on the disk. It works. It actually works pretty well. But there's other approaches that you can use. So another approach that you can use. Now, there are some restrictions. So when you're actually dealing with physical partitions, you may be restricted in the kinds of file systems you can actually install on those actual partitions, because it will have to be a file system type, a physical file system type that the disk actually supports. You can't just install any old physical file system on any old disk. Like, I can't install like a file system from like 1955 on an SSD. It may not, the structure, everything is completely different. It's not to say that there aren't some that you can do that with. It's just there's going to be compatibility issues there. So another really interesting strategy that you can actually do is, instead of actually creating physical partitions on the disk, I say physical, but they're actually logical. It's in code, right? Another thing that you can actually do is, instead of presenting the virtual machine with an actual partition on the disk, you create a file. And in fact, this is what VMware does which is the type 2 visor from VMware. When you actually create a VM in VMware, it actually creates the file system as just a file on the host file system. And then because it is just a regular file on the host system, you can treat the data in that file however you want to treat it. You can simulate and emulate anything. Maybe not fast, but it technically works. So there's different approaches we can take to actually doing disks. We can have the disks and the partitions be just files, or we can actually do real partitioning. Both models work. And I have seen both. If you're wondering what does Sys161 and OS161 do, we create a file. We don't actually create partitions on your disk. We create files. And in fact, I want to say that for any emulator or any type 2 hypervisor, that's generally the approach that's taken, is just creating files. All right. There are some advantages to that, by the way. One of the advantages of creating a file instead of an actual partition is the partition is actually taking the space away from all of the other VMs and all of your other tools. So you can't use it. It's set aside and only that VM could use it. When you take the file-based approach, the hypervisor is setting a maximum file size for that file, but it won't actually necessarily occupy all of that space on your disk unless you actually grow it. So in the end, it actually tends to be, in terms of space usage, it's a little bit better. Now, what about devices? How do we actually handle, button clicks from a mouse or something? How do we know which VM we should actually be sending that to? So there's this concept of pass-through. So what you would do is you assign a device to a specific VM. And the idea is that when you send the interrupt from the particular device, say by pushing one of the buttons on it, what's going to happen is the hypervisor is going to be like, oh, I see this mouse is assigned to this VM, so I will just forward the interrupt to them. It's fairly easy to do. And regardless, there's some basic rules that we want to make sure that we obey. We need to make sure when it comes to devices that we implement device isolation. If I have a keyboard and it is assigned to a very particular VM and I push the letter M, it should only go to the VM that it is assigned to. It shouldn't go to the other VMs that might exist because they might be asleep or they might be doing other things and we don't want to bother them. So it's really, if you're doing pass-through, you need to make sure that you are keeping this isolated from everybody else and not just saying, hey, a keyboard interrupt, who wants it? No. We need to make sure we send it only to the correct one. All right. And in order to do this, by the way, you need more hardware support. So that's kind of fun. All right. So that's kind of an overview of just, we've talked about how do you handle privilege. We've talked about how do you handle virtual memory for both kinds of hypervisors. We've also talked about how to handle disks, I/O, and devices using these different hypervisors. And again, this is a really high-level overview of it. And hopefully it reminds you of some of the course topics we've actually had this term. So now that we ask the question is, why do we use these virtual machines? I mean, there's obviously some performance issues with virtual machines due to the translations, an extra layer of that you have to pass through. Whether it's a type 1 or type 2 hypervisor, it's not as fast as running on bare metal. It's just not. So why do we do it? Well, we do things like emulators, which are our basic kinds of virtual machines. We obviously do that so we can, run MIPS R3000 code on our home machine, or so that we can run old NES games on our PCs. So there's obviously that fun factor that we would do it. Other reasons why we might use VMs is to create sandbox environments. Safe, isolated sandboxes. Now, what do I mean by that? Well, one reason why we create a safe, isolated sandbox in a VM is because maybe you want to develop some Android apps. And you need to make sure, and maybe you don't want to actually do it right on the cell phone itself, because who types on a cell phone like that anyways? I can't. I don't do any typing on the cell phone because it's so tiny. I don't like it. But it's one of those things where it's a pain to do the development on your computer and then have to push it to the actual device to test it. It would be really nice if I could develop and test on the same machine. And that's one reason why we use virtual machines, is to create a cheap sandbox environment for you to test the programs when you don't actually have the physical hardware in front of you, or it's inconvenient to do the testing and development on the actual physical hardware. So developers for iOS or for Android tend to use an emulator or a VM to actually do the development and testing right on their host machine. Another thing that you might is maybe you've downloaded an application from a less than savory website and it's a program you really need, but you're afraid that if you install it natively that there might be a virus, and if there's a virus it's going to take out your whole system. So what do? You create a VM and you install it in the VM because it will be this nice isolated sandbox. It's protected. If you get a virus in the VM, who cares? You'll just delete the VM. Bye bye virus. You still get to use the program, or at least you get to test it. So that's another reason why we actually have virtual machines, is to create safe places to use less than savory software, or to test less than savory software. Another reason why we've used virtual machines, and this is actually something that's only been for the last 10 or so years, is resource utilization. So you might be aware that Amazon and Microsoft and Google and a whole bunch of other places actually allow users to purchase time on their servers and use them. And they're you're paying for a virtual machine to run on their machines, on their servers, and you pay by the hour. And it's really great. You know, if you don't want to set your own computer on fire, set somebody else's on fire. And I mean, but, you know, back when I was a grad student, I didn't have the best computing resources. And the computing resources that I did have, I didn't want to ruin. And I knew that if I ran GPU code on them, that the chances of me destroying them, due to my previous experiences running GPU code on them, was probably going to result in overheats, which eventually takes the machine down. So instead of running things on my own computer, what I decided to do was rent time on Amazon. So even though, you know, it costs, you know, a few dollars a day, if you only need it for a week, at least you're not destroying your hardware. And I mean, Amazon actually had a free tier at the time where I think you get like 750 hours a month of the lowest level tier. And if you just need an extra machine to do some computation work, it's a pretty cheap and effective way of doing it. But how did this even become a thing? Amazon used to be where you bought textbooks and music from. Okay, a really long time ago. Now they sell everything. So my understanding of what happened was, if you look at sales on Amazon throughout the year, there are periods of time, obviously around Christmas and holidays, any gift-giving season, where the traffic to their website skyrockets. And in order to handle the demand during those shopping seasons, they had to add a lot more infrastructure. So more data centers, more computation power, more space to store things. But then in down seasons, like, well, there's no holidays in June or May. I mean, the only thing people buy for the May 2-4 weekend, which I guess is called Victoria Day to most people. I'm from the country. We call it May 2-4 because the only thing people buy on the Victoria Day weekend is beer. So, I mean, what happens to all that extra infrastructure that Amazon bought to handle the holiday seasons during off-season? Well, it just sat there idle. So they had this idea, and this is my understanding from a paper I read probably 10 years ago, was that Amazon was like, wait a minute, what if we rented time on our servers? So through this VM, they can actually they can get some money, but they're also making better utilization of their resources. And then, of course, it really takes off, and everybody now offers this as a service because it's a really great idea. And it's really great for users and small companies because they don't have to invest in the infrastructure. They don't have to maintain it. They don't need the space for it. They just pay somebody else to do it for them. And at the end of the day, for many companies and many individuals, it's just cheaper to let Amazon or Google or Rackspace or whoever handle it for you. And it's all done with virtual machines. Now, for them, they're probably using type 1 hypervisors. Better performance than type 2. But it's still the same idea. Other reasons why you might use virtual machines: checkpoints and snapshots. So you can actually, as you're, using your little VM, you can make a snapshot. You can save the state. And then you can continue on your way. And then when it crashes, instead of being like, oh my gosh, it crashed, you go back to the checkpoint. You go back to the snapshot. Pretty cool, eh? So it's kind of like you can go back in time. And that's a pretty cool feature as well. All right. So that's actually the end of the official course topics. So nothing after this point will be on the final assessment. For those of you that are actually curious about the final assessment, what format it has, it is a quiz on learn, just like the ones you've been doing the whole term. It's obviously a little bit longer because, it's a final assessment. And if memory serves me, you get some number of attempts. Let me just check here. So let's see. You will get just checking. So you get 240 minutes to do it. I think that's like 4 hours. Hey, that's longer than a real final, right? The reason why we give you so much time to complete it is actually because we don't know where you are living right now. We don't know what your home situation is. We don't know what your internet situation is. I'm going to make the assumption that you all live in the middle of nowhere and you all have dial-up internet. And I know what that is like because that is what I grew up with. So we tried to make the final assessment fair for individuals who are living in remote wherevers. So you get, looks like 240 minutes to do it. And you are going to get 2 attempts. And each attempt is going to be different because there's a giant pool of questions. And you get, so many from this level, so many from that level, so many from this level, and so on and so forth. So each attempt, you're going to get a slightly different paper. And you get 2 attempts. You don't have to take both attempts. Immediately when you have completed the attempt, you will know your score. You will not know which questions you got right or wrong, but you will know your score. And then based on that score, you can decide whether you want to take a second attempt or not. It's totally up to you. We will take the highest attempt score. So if you don't like your first score and you do it again and you get like 10% better, you get the higher grade. We don't want to stress you out over this. The other thing that is important to note is that the final assessment will actually be available for not, just one day. It's actually available for the entire exam period. So the final assessment will open up on August 7th and it's due on August 16th. So that's about 9 days that you have to do it. Why are we giving so many options and so much flexibility? Again, I'm going to make the assumption that you all live in rural Ontario or Saskatchewan and you don't have proper internet access. I'm going to assume that you're using a dial-up modem on a 486. And I want to make sure that wherever you are in this world, whichever time zone and whatever kind of internet that you have a fair chance of actually completing the final assessment. It is an open book assessment. You can use the videos, you can use the course notes, you can use the guides on Piazza. The only thing we ask that you don't do is sit there and talk to each other on Discord. We are not going to be using any kind of proctoring software because that's both an invasion of your privacy and it's installing a rootkit on your computer. And, we're teaching OS here, so making you install rootkits on your computer is kind of insulting. So we're not going to do that. So we are going to take your word for it that you are being honest. So please do. But hopefully that will make things a little less stressful for you. The other reason why we're giving you 9 days to actually start and finish it is because we don't know when your other finals are scheduled for. So we want to make sure you have the maximum flexibility to make this work with the schedule that you have. We're not trying to stress you out. We're trying to make this easy for you in a time where everything is kind of stressful. So that's the final assessment. In our next episode, we are going to, there is one more, it's Tuesday of next week, because every term is 24, and that's what you've paid for, so that's what you're going to get. We're not going to short you on any episodes. We will be talking about networking in your operating system. It's going to be a pretty high-level discussion, just to kind of show you how some other devices and tools are integrated into the kernel and the user program. It's up to you. You don't have to tune in, but you can if you want. And either way, if you received a course evaluation, please make sure you fill that out. They're not really for the instructor anymore. I don't even receive them at the end of the term. They're mostly just curious about how is the online offering. But please do fill it out if you get an opportunity. And yeah, if you decide not to tune in for the final episode, I really do hope that you have a good rest of the term. So either way, networking in episode 24, and we'll see you next week.